Hi guys. This could be lesson C-A10 if that's in your booklet, or C-B1. I'm getting mixed reviews from you guys as to whether or not it's in your A booklet, but I definitely have it in the B booklet. So if it's not printed off from the B notes, hopefully you've printed all of the chemistry B notes by now and you're ready to go. So this will be the first lesson and there is a worksheet to go through after that. So just make sure you have your periodic table and your notes ready to be filled in. So let's get going here. Use purple again. Full screen. All right, so I have this as CB1 right now, but again, it could be CA10 in your notes package if it was in there. So we're going to be talking about properties of acids and bases. Usually a lot of this is demos at school, but that's not really going to happen. I would recommend looking through some of the CBE online for some of the demonstrations and just a little bit more information, but I've recommended that through every step of the way. So if you're a little bit stuck on anything in Chem A, maybe go back through. They're posted on D2L and in the Chem A part in a separate folder called CB Online Stuff, I believe. So just look for that. So first we're going to talk about acids. So our general way that we'll kind of describe it is most acids have hydrogen in front. The big thing though is all acids are aqueous. So we'll talk about what aqueous means. That'll be important in chemistry B as well. So they can be solids, liquids, or gases as pure substances at room temperature. So an example is hydrogen chloride gas. So again, our nomenclature from the first part doesn't disappear. If you're still struggling with it, we need more practice. So hydrogen chloride, when they are dissolved in the word, or when they are dissolved in water, we say that they ionize. And so you see the word ion in there. So that means that when we're talking about something ionizing, it means that it forms ions in solution. So when hydrogen chloride gas, so that's what this little g means here, when hydrogen chloride gas dissolves in water, it actually produces hydrogen ions, so H positive, and those chloride. So the chlorine ions, chloride, is Cl with a 1 minus. So that's represented again as HCl aqueous. So we don't say that it's produced H plus and Cl minus, but we say that it is represented as hydrogen chloride aqueous. So aqueous again means that it's dissolved in water. So this would also, we talked a little bit about dissolving in water, and if it produces ions that it will conduct electricity, whereas if we dissolve sugar, so something like sucrose, which you guys should have memorized, if we dissolve it in water, it doesn't actually form ions. It just isn't the big particles that you can see. It will still be sucrose though. So therefore, acids ionize in water to produce H plus ions. They are aqueous. I feel like we've already said a whole bunch of that. So dissolved in water. Bases are different, are usually ionic hydroxides. So you'll probably recognize the word hydroxide as that polyatomic ion OH with a 1 minus charge, so containing the OH negative ion. So when they are placed in water, we say that they dissociate. But again, for the level that we're going to be talking about right now, ionization and dissociation are really similar situations in what they are forming. So sodium hydroxide, so again, sodium hydroxides, the polyatomic OH is our hydroxide ion. When we put it into water, it produces sodium 1 plus ions and the hydroxide 1 negative ions. And so again, we have an aqueous solution here. So therefore bases dissociate in water to produce OH ions. So that's the important part. So when we're talking about hydroxide and when we're talking about hydrogen. So acids in water ionize to form those H plus ions. Bases dissociate to form those OH minus, OH negative ions, so aqueous as well. And so this is kind of a general definition for acids and bases. There are exceptions to these rules of forming hydrogen ions and forming hydroxide ions. Um, and in Science 30, we talk a little bit more about acids and bases. So moving on. So the pH scale, you've probably heard of the pH scale. So pH is a measure of acidity. So it stands for, what pH actually stands for is the power of hydrogen. So the pH scale ranges from 0 to 14, which is an expression of the concentration of those hydrogen ions in solution. So it indicates whether a substance is acidic or basic. So the more acidic the substance, the lower the pH. And so something with like a pH of 0 to 3 are considered to be what we'll call strong acids. And again, we don't talk too much about this in Science 10, but in Science 30 we look at relative strength of acids, relative strength of bases, and go a little bit more in depth. So the more basic a substance is, the higher the pH. So something like a pH of 12 to 14 are considered to be our strong bases. And so neutral substances have a pH of approximately 7. So we call a pH of 7 neutral. We call anything below a 7 acidic. So acidic is below a 7, basic is above a 7. And again, like these are our strong bases. These are our strong, our strong acids. And these we'll call a weak acid. And so thinking about that, if you look at our strong bases, so ammonia solution, bleach, oven cleaner, those are still quite corrosive. We always think of acids being the only thing that are corrosive, but these can be very corrosive as well. Um, so those are things that you don't really want to be drinking. If you look at lemon, like things like lemon juice, it's very acidic, and yes, we eat it. Your stomach acids, so the secretions by your stomach that help you to digest food, is very acidic. So it's kind of between a 1 and a 2. Battery acid is somewhere right around a 1, I believe, on the pH scale. So these are things that are quite corrosive and quite tough. If you are to get it onto your hands, it's not great. And then things that are normal around the neutral thing, like milk is slightly acidic, your blood is slightly basic due to buffers within your blood. Um, so that's kind of the general pH scale. Flipping over to my next page, I don't know if it's the same on yours. We'll talk a little bit about indicators here. So indicators, and you can have acid and base indicators, and those are chemicals that change color in response to the concentration of hydrogen ions or hydroxide ions in solutions. So these are some type of chemical substance or something that you can use to tell you whether something is acidic or basic. We can even go more in depth, so we can use indicators to tell us kind of the approximate pH of things. So in your data booklet, I don't have one in front of me. I think I put it in, but it's something we definitely use in Science 30. There are indicators that if they turn a particular color, so I'm looking at the one in mine. I don't think you guys actually have it. It's on page 12 of the data booklet, so I don't know if I actually gave you guys it. But there's something called, let's look at bromothymol blue. So if we put it into a substance and it stays or it turns yellow, we know that the pH needs to be less than 6. If it stays blue, the pH needs to be greater than 7.6. And if it's some type of green, let me be writing this down. I don't know, I'm thinking of it. So and so, sorry. I was saying it, but not writing it. So 6.0 to 7.6. And so if it is yellow, it's less than 6 on the pH scale. So this is less than 6. We don't know if it's a 5 or if it's a 2, but we know that it's less than 6. If it is greater than 7.6, it actually ends up blue. And if it's in between here, this is, again, Science 30 stuff, but it's kind of interesting. If it's in between there, it's actually green. And that's kind of your art color wheel stuff. That kind of the mixture of yellow and blue will end up being green. So if we put it into a colorless solution and it turns green, we know that the pH needs to be between 6 and 7.6. So indicators, again, are used to indicate whether a substance is an acid or a base. Most look like water, so they are colorless to start. A lot of them, not necessarily all of them. This one here is actually quite blue to start. But a common one that you've actually probably seen used before is called litmus paper. And so these are little strips of paper essentially. There are two different types of litmus paper. So there's blue litmus and red litmus. And usually when you're testing something, you're going to actually use both strips. So if you take a blue litmus and it turns red, we know that we have an acid. If you have red litmus and you dip it in and it stays red, we know we either have an acid or we have something that's neutral. If we take red litmus and we dip it in something and it turns blue, it is going to be a base. If we take red litmus and we dip it in something and it stays red, we know we either, sorry, I'm mixing myself up here. If we have blue litmus and we dip it in something and it stays blue, we either have a base or we have something that's neutral. So these little strips of paper, they're like super tiny, like smaller than your pinky finger. That just tells us whether something's an acid or a base. But again, usually we're going to use both of them because again, if you dip red litmus in something and it stays red, you don't know if you have an acid or if you have something that's neutral, so you kind of need to do two of them. It says complete the following table which compares some of the observable properties of acids and bases. See page, mine says page 66 in the textbook, yours says 64. You don't have a textbook, so that's not really going to help. I think what I'm going to do is type in this one. Just makes things a little bit easier than trying to write on this tablet that I have. So looking at this, so again, some of the properties of acids and bases. Acids typically taste sour. Um, so just kind of some examples. We saw there lemons, limes, talking about the juice of them, not eating the rind of it. Vinegar. Whereas bases tend to taste bitter. Um, so quinine in water, so something like tonic water actually has this substance in it. It's an interesting chemical and it actually has a pretty bitter taste. There's not a lot of bases that you necessarily consume. If you looked at eating some um, baking soda, it would probably taste pretty bitter and it's definitely basic. But usually, like in the lab, you're not going to be like, I'm going to test if this is an acid or a base by eating it, but this is just kind of some general properties. Um, so, so acids, some other kind of properties for them. So how they feel. So if you have something that's acidic, many acids will actually burn your skin. Even things like lemons, if you get lemon juice on your hand, or if I don't have another example for it. It'll do a little tiny bit of damage to your skin, right? You won't really notice it. But again, if you get battery acid, so something with a really low pH, it's very corrosive to your skin. If you have some of the acids that we have in the lab, like something like sulfuric acid, that will definitely burn your skin real good. But Same thing here, many bases, especially if we're talking about, again, strong acids and strong bases. Many bases will also burn your skin. So in the lab, something like sodium hydroxide. Sorry, it's going to just keep capitalizing stuff on me there, and I'm not going to keep going back. Bases as well, they usually feel slippery. So something kind of like soap where if you have bases on your hand, it feels a little bit slippery instead of tacky or hard to move around. Um, I don't know that I want to finish. Let's keep writing. Indicator tests. So for an acid, red litmus stays red, whereas for a base, red litmus turns blue. For an acid, blue litmus turns red. For a base, blue litmus turns blue. Stays blue. Some of the other ones that we usually use when I'm doing demonstrations and stuff is something called phenolphthalein. And I always have to look at the spelling because there's way more consonants in a row than you want. So phenolphthalein in an acid actually turns colorless, whereas in a base it actually turns this really kind of bright pink. And for the most part, so as I described before, bromothymol blue turns yellow with acids and turns blue with bases. Bromothymol blue. It stays blue with bases. Chemical properties. Sorry. Hopefully you've paused the video if I'm typing too fast. Just is a little bit easier and clearer to read than when I try to write with this tablet for bigger writing sections. Chemical properties. So acids tend to corrode metals. Usually producing hydrogen gas. Other chemical things that they can do is they can neutralize a base. So if we mix an acid and a base, it produces a neutral substance. Bases, for the most part, do not react with metals. And bases can be used to neutralize an acid. All right, so that's the chart. So pause it if you need to. I'm going to go on to the next page where it's talking about naming bases. So naming bases. So again, the way that we described bases is that they contain a hydroxide compound, so that OH negative part. So it means the formula for a base always contains at least one OH minus and only acts as a base when placed in water. Bases are super easy to name because we've already done it. Bases are simply named like ionic compounds. So you would have seen this before. We have sodium, we have hydroxide, one of our polyatomic ions. So the way we name it is sodium hydroxide. The only thing that will make it clear that we're talking about a base is this aqueous. Sodium hydroxide, not dissolved in water, is actually, I'm trying to write with my tracker pad instead of my tablet here. So sodium hydroxide actually comes in these little pellets, like when they get shipped to us. I could show you again if we were at school. They're these little like bigger than sugar, but kind of pebble-sized pellets that they send to us for creating this base. So it's a solid at room temperature, but aqueous again is talking about dissolved in water. So kind of one of our exceptions um, is ammonia. So NH3, this is one of your memorized molecular compounds. So ammonia acts as a base but has no hydroxide. So again, you'd see it as, and we just name it the same way that we've named it before. So NH3 being ammonia, not nitrogen trihydride or anything like that. It is ammonia. Naming acids is a little bit more complex than bases, since we already knew how to name bases. So naming acids gets a little bit more complex. So the way that we name these, this chart is going to be really quite helpful. So we name the hydrogen compound as if it were just an ionic compound. So HCl, we've seen that before. HCl, we name it as an ionic compound. So we name the first element full, so hydrogen, second element with the ending changed to IDE, so hydrogen chloride. If this was a polyatomic, we keep the ending the same. So change the ionic name to an acid name using the rules below. So the endings are key here. So this is what we have here, this first one. So hydrogen chloride. If this was our ionic name, sorry, tickle in my throat. So HCl. So that's hydrogen chloride is how we would name it in an ionic compound. So if we had HCl, that's a gas, I believe, at room temperature. We name that hydrogen chloride. If we now have HCl aqueous, so again, it's dissolved in water, the way that we name it is we keep the beginning of hydro. So you can see that you're kind of ditching, oops, ditching the gen of hydrogen. And whatever you had here kind of goes in this spot here. So we had hydrogen chloride. So the way we name it is hydrochloric. So that IDE ending becomes ic, hydrochloric acid. So the next one is hydrogen nitrate. So nitrate is NO3 with a 1 minus. So if we had, oh, I don't know what state this is, we'll say it's solid. If we had hydrogen nitrate, we would name that again hydrogen nitrate. But now if we have HNO3 aqueous, the way that we would name that is we ditch this whole hydrogen part. And again, remember that part that's kind of blocked out with the dots here is nitr. So the way that we name this is nitric acid. So you see here, there's no hydro in front of it. So when the ending is ATE, it just becomes ic. When the ending is IDE, it's ic, but we see there's a hydro in front. So that's a differentiation we need to make. And then the last one, hydrogen nitrite. So nitrite is NO2 with a 1 minus. Again, I'm just going to call this solid for this purpose. HNO2. So if we now have aqueous, so an ending of ITE, again, these ones are just going to be from polyatomic. An ending of ATE and ITE come from polyatomic. Again, IDE comes from like on the actual periodic table, right? You change the ending to IDE. But if we had hydrogen nitrite, it becomes nitrous. So now we have an ending of OUS. So ite becomes us. So we'll just do a couple of examples here. Oh, in your book you might have had blanks here. My book has that. I don't know why this set of notes does have it filled in. It's all good though. So HF aqueous, so again, seeing this aqueous paired with that H in front, I think I'm missing an example here. Oops. So first, let's practice just naming just an ionic compound. So HF would be hydrogen fluoride. So I see the ending IDE. So we know it's going to have that hydro. And we know it's going to be ic acid. And so again, this part is going to be fluoric, hydrofluoric acid. So that fluor part here ends up right in here. So hydrofluoric acid. These, just as a note, shouldn't be capitalized. Any of these. Word seems to like to add that on if it's the first thing in a sentence, but they should not be capitalized. Next one, so H2CO3. So in order to name that, again, hydrogen, CO3 with a 2 negative is carbonate. So this is my ionic naming. And over here is my acid naming. So hydrogen carbonate, so that ending of ATE is going to be the second rule, that what we just take is this part and then add ic acid after. Carbonic acid. Carbonic acid. And so the other example that you guys might have in your notes package there is H3, BO3. And again, that's aqueous. I didn't leave myself room. So naming that hydrogen, and that polyatomic is borate. I thought it would be the other naming rule, but it's the second naming rule again. So hydrogen borate is boric acid. Because again, this bor part becomes ic acid. So just a couple kind of exceptions that come up just with the naming. So some of the exceptions are acids that involve sulfur and phosphorus. Just sometimes it sounds a little funky, so I'll show you in a second. So acids containing sulfide. So again, sulfide is that S2 minus ion. So acids that contain that ion in solution, that sulfur ion in solution, we add the altered ending UR. So H2S, hydrogen sulfide. We actually name it, so hydrogen sulfide. So that part that was kind of blanked out with the dashes is sulf. So we actually wouldn't name it hydrosulfic acid. Again, this ic and this hydro are always the same, but that sulf came from this sulf. So the way that we actually name it is we add back in the U and the R of sulfur. So now it's hydrosulfuric acid, not hydrosulfic acid. Hydrogen sulfate, so ending ATE, we know changes the ending to IC, but again, that sulf part of it is here, and we actually re-add in that UR of sulfuric or of sulfur into it, sulfuric acid and sulfurous acid for hydrogen sulfite. Same sort of idea with phosphorus. So hydrogen phosphide. So hydrogen phosphide. So again, the part that would carry over is this part, but you see that we add OR back in. So instead of being hydrophosphoric acid, I guess that's what it would, hydro, phosphoric acid. No, that's not actually right. So it's hydrophosphoric acid. So that OR and that UR come back into play for sulfur and phosphorus containing compounds. Just keep that in mind. Try to stick with that if you come across it. Um, Sometimes another exception of something that you will see, pardon me, is organic acids. Again, these don't really come up a whole heck of a lot. So these are acids that contain carbon and hydrogen. And so you see with all of the other ones, we always have that hydrogen at the beginning. If I could scroll back, this one actually contains hydrogen at the end of the formula. So this is one of your memorized ones. This is acetic acid. You had that memorized from the molecular compounds. So this acid contains the acetate ion. That's this. It's in your periodic table, I believe. So it contains the ion CH3COO with a 1 minus, and then that has that hydrogen ion that can ionize within solution. So just another exception of something that you might see. So writing the formulas is kind of a working backwards process. As I've mentioned before, Alana loves weird ways to remember these things. So this is actually from her. So in order to write the formula of acids, you need to work backwards from the name. So the following may help you remember how to name and write the formulas for acids. So she says, hide a hickey. So if it has H, so hydroic, then it's an IDE ending. If it just has an ick, so ate an icky, sometimes we do that. You eat something icky, so ate an icky. So if it just has an ick ending, that is an ATE ending. And you want to bite something that's delicious. So if it has an OUS ending, it is an ITE. So working backwards from these, so ick and hydro, so ick and hydro, so since it has that hydro at the beginning, that's going to be an IDE ending. And so I see this iode, so we know it's going to be hydrogen. And this iode again, that part's coming from right here. So iodic, so hydrogen iodide would be our ionic naming. So hydrogen, we know, forms a 1 positive charge, iodine forms a 1 negative. So in order to write the formula, we know that that would balance out with a 1-to-1 ratio. So hydrogen iodide, we put aqueous beside it though, that makes it hydroiodic acid. Nitric acid, so there's no hydro here, so it's just the ic ending, so we know it's going to be ATE. ATE ending, so hydrogen nitrate. So again, hydrogen forms a 1 plus, nitrate forms a 1 minus, so our equation would be HNO3. And again, we want to specify that it's aqueous to be talking about an acid. And this one, hypochlorous acid. So don't be fooled by this hypo at the beginning. That's not hydro. So hypochlorous acid. So we have an ending of OUS. Again, the ending of OUS is ITE. So that's going to be, there's going to be hydrogen, but then we're going to have hypochlorite. Again, this ending of OUS means that we're going to be talking about ITE ending. I should say ITE. So hypochlorous becomes hypochlorite, and you want hydrogen there as well. Hydrogen forms a 1 plus. Hypochlorite is ClO, I believe just 1 minus. So it should be HClO. And again, that is aqueous. So that's writing formulas of acids. So naming and formulas, there is a worksheet for you guys to work on. And thank you for that. See you later.